Howdy AP students, this is chapter 13, lesson 2. In this video we're going to cover the reaction quotient and we're going to relate that to the equilibrium constant, and then we're actually going to practice by calculating the value of Q, and then we're going to utilize R.I.C.E tables in order to calculate equilibrium constants or the equilibrium concentrations. So in 13.5 we're going to cover the application of the equilibrium constant. So when working with equilibrium problems, it's not always obvious which way that the equilibrium is going to shift. Obviously, if the initial concentration of products is 0, we're going to have to shift to form products. However, if there are reactants and products present in the reaction, you must solve for which way the reaction is going to go, which is where we get Q, the reaction quotient, to determine which way it's going to go. Q is calculated like the value of capital K, the equilibrium constant, but we're going to use, and I'd like you to box this in if you've got your notes with you, the initial concentrations instead of the equilibrium concentrations. So a couple things to know. If K is equivalent to Q, then the system is already at equilibrium. It's not going to go anywhere. Sometimes we will show arrows of the same size. If K is less than Q, then the product to reactant ratio is too large and the equilibrium is going to shift to the left. So sometimes you'll see a big arrow and a small arrow for that. If K is larger than the reaction quotient, then the product to reactant ratio is too small and the system has to shift to the right. And sometimes what we'll see is a small arrow and a big arrow that way. So let's go ahead and put that into play. Let's practice calculating the equilibrium reaction quotient. For the synthesis of ammonia, the value of K is 6 times 10 to the negative 2 at a certain temperature, 500 degrees. In an experiment, 0.5 moles of N2, 1 times 10 to the negative 2 moles of H2, and 1 times 10 to the negative 4 moles of NH3 are mixed at 500 degrees Celsius, and you'll notice that's the same temperature, so we can use the K value. And it's mixed together in a 1-liter flask. In which direction will the system proceed to reach equilibrium? Well, the first thing we need is a balanced chemical equation, which is found in the notes. What we know is that before anything mixes, we have initial concentrations, and I'm going to go ahead and write those below the reaction. Now, we got to be careful because in the problem, moles were mentioned, but we're going to be using equilibrium concentration. So let's refresh that brackets equal moles per liter. We're lucky in this case because the volume of the flask is 1 liter. So if it wasn't, we would have had to do a division to make sure it was the correct concentration. Next, we need a equilibrium expression. In this case, we're going to use the letter Q, capital Q, for the reaction quotient. Remember that the coefficients are the exponents in our equilibrium expressions. And we have products over reactants. What we did not cover that I want you to add to this is that all of these are in the gaseous state. Remember that we can include gases and aqueous systems in equilibrium, but we cannot include solids and liquids. When we plug in our initial concentrations and we solve, we get a value of 2 times 10 to the negative 2. Now remember, units we could calculate, but they're not necessary. The value of Q is what is important to us. So if I compare 0.02 to the initial equilibrium constant, 0.06, this is Q and this is K, you'll notice that K is greater than Q. And in that case, the equilibrium is going to shift to the right, which means we are going to form more products. This is going to help us formulate our R.I.C.E tables eventually when we get there. So let's talk about that. How do we solve equilibrium problems? This is chapter 13.6. When solving equilibrium problems, it's very important to follow a series of steps. skipping these may lead to some issues and possibly fewer points on your AP exam. So here are the steps for solving equilibrium problems. Number one, you're going to want to write a balanced equation. If a chemical reaction occurs, work out the stoichiometry, and then here it says to write out a second equation. That's probably so that we can only include what's important to us at equilibrium, gases and aqueous. Always do the stoichiometry first. That's going to be very important. Step 2, set up the equilibrium expression. Remember that capital K is equal to products over reactants. No numbers yet on that. Step 3, if you can't tell which way the reaction is going to shift, we're probably going to have to do what we just did and solve for the reaction quotient. And remember, it's going to be the same, products over reactants, but with initial values. Step 4, we're going to set up a R.I.C.E table, which is the initial concentrations, the change in concentrations in terms of X, and the equilibrium concentrations. So I is for initial, C is for the change to get to equilibrium, and E is for the equilibrium. So what does R stand for? R stands for the reaction. You're going to have that reaction. Step 5, substitute equilibrium concentrations into the equilibrium expression, and then we're going to solve for X. Sometimes X will be given in the problem. Sometimes we are solving for the constant, and sometimes we have to find the change. And then number 6, check your answer to make sure that it is logical. If we are shifting to products, we should see an increase in the amount of products. If we're shifting to the reactants, we should see a shift in the amount of reactants. Okay, here is our first example. At 700 Kelvin, carbon monoxide reacts with water to form CO2 and H2. The reaction is given. It's a 1-to-1 ratio. The equilibrium constant is given at the same temperature, 5.10. Consider an experiment in which 1 mole of CO, 1 mole of H2O are mixed together in a 1-liter flask. Calculate the concentrations of all species at equilibrium. Okay, so let's set up our first R.I.C.E table. The box is in your notes. The reaction is written. The initial values that we are given for the reactants are 1 mole. And we have a reaction vessel that is 1 liter. So 1, remember, 1 mole per 1 liter. We need to make sure that we're plugging in the right things here. There are no products. Doesn't mention anything about products, so we can assume the reaction vessel is empty before we begin. Because this is the case, we know that equilibrium must shift to the right to form products, which means K is going to be greater than Q. We don't even have to solve for it. The change in X is based on the stoichiometry. We know because we're shifting to the right for products, we will be decreasing the concentration in CO and decreasing the concentration of H2, and we will be increasing the concentration of CO2 and increasing the concentration of H2. Keep in mind that if we had a 2 in front of CO, it would need to be 2x. But because everything is a 1-to-1 ratio, we can leave it as a single x. So the equilibrium, we basically almost have a line here for addition and subtraction, and we're basically putting these together. So at equilibrium, 1 minus x will be the change for carbon monoxide, 1 minus x will be the change for H2O, and positive x's will be for CO2 and H2. We will write our equilibrium expression, products over reactants. Everything is a 1 or a first exponent. When we plug in the values, what we got here was x times x over 1 minus x times 1 minus x, which is why you see the squared terms here and here. To solve, we can take the square root of both sides, which allows us to cancel the squares. And then we're going to solve for x. using algebra. And what we find is that the value of x is 0.69. This is the variable that we can use now to plug in back into our equilibrium and find the concentrations. So because x was what CO2 and H2 was, that will hold constant for the reactants, but we have to do a subtraction in order to find what the reactants are now, which is 0.31 molar. So here are the final equilibrium concentrations. Next example, we have phosphorus pentachloride gas decomposes to form chlorine gas and phosphorus trichloride. At a certain temperature, a 2-liter flask initially contained a 0.298 mole of PCl3 and 0.00870 moles of PCl5. After the system had reached equilibrium, 0.002 moles was found in the flask. So what we have is an equilibrium concentration. Calculate the equilibrium constant for this reaction. So here we're solving for capital K. In the last problem it was given. In this case, we're solving for it. So I'm going to set up a R.I.C.E table. First thing I need is to know what was given in the problem. I have to be careful because the flask is 2 liters. So to find our concentrations, I need to divide moles per liter. So these are the values that will be plugged into the R.I.C.E table. R.I.C.E, R is for the reaction. PCl5 gas yields PCl3 gas plus Cl2 gas, and it is balanced in a 1-to-1 ratio. The initial concentrations are shown here. Remember that this is moles per liter. No products were mentioned for Cl2 gas, so we can assume 0. The change in concentration, because there is 0 chlorine, we know that we have to form products. Otherwise, I would have to solve for Q. So once again, K must be greater than Q. I will be decreasing the value of PCl5 and increasing in values for PCl3 and Cl2 gas. At equilibrium, this is what I will be given. Because I know in the problem that 0.00200 moles of Cl gas was found in the flask, I can sub it in for X, but I have to be careful because it was a 2-liter flask. So 0.002 moles of Cl2 divided by 2 liters gives me 0.001 molarity. So I can take that information and I can plug it in for the equilibrium values and solve for the concentrations at equilibrium for each substance. Now that I have the equilibrium concentrations, I can plug them in to the equilibrium expression and eventually solve for KEQ. When I plug in the values, KEQ ends up being 0.0448. We could calculate units, but we are not concerned with the units here. Next problem. Consider the reaction 2HF gas yields H2 plus F2, where K equals 1 times 10 to the 2 at some very high temperature. In an experiment, 2.5 moles of HF, 2.5 moles of H2, and 2.5 moles of F2 are mixed in a 5-liter flask and allowed to react at equilibrium. Solve for the equilibrium concentrations. Well, first thing we need would be a reaction. In this case, we're going to go ahead and solve for the concentrations. We have a 5-liter flask. So here are my initial concentrations. And you'll notice that I have amounts of reactants and products. There are no zeros here. So I need to figure out which way the reaction is going to proceed. So I have to use the reaction quotient Q. Products over reactants. It's a 1-to-1 ratio, except for HF. You'll notice that it is a 2, so we have a squared term on bottom. When I plug in the concentrations initially, Q ends up being a value of 1. They said that K was equivalent to 100, which is greater than 1, so the equilibrium reaction is going to be shifted to the right. I'm going to set up a R.I.C.E table. 2HF yields H2 plus F2. Initially, I've got the same concentration for all products and reactants. The change, and I want to note, because we're shifting to the right, we will be consuming reactants and forming products. We have a 2x here because the stoichiometry was a 2. Equilibrium is going to be as follows. 0.5 minus 2x for HF, 0.5 plus x for H2, and the same for F2. I'm going to take those values, plug them into the equilibrium expression, which is the same as Q, but this is at equilibrium. We know the value of K, and we have our new equilibrium values. Keep in mind that H2 and F2 are the same, which is why this is a squared term. I take the square root of both sides to simplify. I cross multiply, distribute, combine like terms, and solve for x. X is 0.21. When I plug this value into my equilibrium positions, the concentrations of H2 and F2 are equivalent at 0.71. And we can go ahead and put units on that of moles per liter. And HF is 0.080. Again, moles per liter. In the next problem, we are going to look at something we call the negligible x. In certain equilibrium expressions, some plus x and minus x values can actually be treated as negligible, and that is because if the value is less than 5% of the number that it was to be subtracted from or added to, then it's not going to change any of the values at equilibrium. The value of x is considered negligible when the value of k is very small. If k is small, very few products are formed, so x is going to be a very small value. Most of the problems we'll encounter, x can be negligible, but always check your answer to be sure it makes sense. Gaseous NOCl decomposes to form nitrogen monoxide and chlorine gas. 0.65 moles of NOCl is placed into a 2-liter flask. What will be the equilibrium concentrations for each species in the reaction? We've seen an example like this, but we're going to look at a negligible X problem. Initially, I have 0.65 moles, and I'm going to divide it by 2 liters to find the initial concentration of NOCl. I'm going to set up my R.I.C.E table as follows. Reaction, make sure it's balanced. We have a 2 to 2 to 1 ratio. Initially, I have 0.325 molar and 0 for the products because it was not stated in the problem that we had anything. The changes will be as follows. Reaction must proceed in the forward so that we get a negative 2x for NOCl, positive 2x for NO, and positive x for Cl2. The equilibrium positions are here, 0.325 minus 2x, 2x, and x. My equilibrium expression, I can plug in my values as we did before. And here is where we're going to find ourselves a negligible x. On top, we will have an x cubed term, and on bottom, we will have an x squared term. In this case, if the powers are off, chances are we will have a negligible x here. It's not going to affect the value of the problem. So we will solve without using the 2x in this problem. 0.325 squared gives us 0.106. And then we solve like normal to get 0.0075. Plugging in to the equilibrium positions, I will find my equilibrium concentration for each species.